Yeah, so good afternoon, and let me first begin by thanking the organizers for year after year organizing this wonderful community meeting. It's a great place to meet everybody, okay? Old friends and new friends, okay? So I'm going to talk about some work that has been going on in the group, okay, on liquid crystals, okay? And this time I'm going to talk about a different type of liquid crystals, and these are achiral objects, okay? They're bent objects, and they give rise to some nice chiral phases, okay? So, brief outline. Okay, let me first tell you a little bit about pneumatic and bent core liquid crystals because I did not see any talk on liquid crystals this time. Okay, then we go about with chiral phases of the bent core molecules. I'll tell you about some coarsening experiments that we have done, certain observations that were unusual, and the future perspectives or the future directions that the group has been taking. And you can see this banana here. So these bent core liquid crystals are actually banana-shaped liquid crystals. They're these curved objects, achiral, but let's see what kind of phases they give. Okay? And this was part of Nishan's PhD thesis, co-supervised by my colleague in JNU, Sanjay Puri. And it was also part of a UKRI project that we had. The partner there was Nigel Wilding. Okay? And it's been published in this particular paper. Okay? So many of us are familiar with pneumatic liquid crystals. So liquid crystals, as you know, are intermediate between conventional solids and liquids, and they combine fluidity with long-range orientational order. Okay? So these are the different phases that one could have. This is what you have in a crystal. You have a perfect periodic order. Okay? In liquid crystals, okay, you have a long range order, but they're fluid, and that's the isotropic liquid. What you see on this axis here is the temperature. Okay? So in the pneumatic phase, the molecules are usually rod-shaped molecules. These are called calamitic liquid crystals. They could also be discotic molecules, and they have a tendency to self-align in a certain direction. Okay? And that direction is what is usually known as the director of the system. Okay? So that's the natural direction in which all the nematogens would like to align. Okay? And of course, we know this last statement that they have a very rapid optical response to even the tiniest of electric fields. And that's the reason why we are exploiting them in LCD optical switches, optical imaging, and so on and so forth. Okay? Now, these materials, they have inherently, they have elastic and they also have inherent topological defects. Okay, so for example, these are the kind of distortions one usually finds. Okay, this is what is called as the splay distortion when the liquid crystals are aligned, spread out like our hand, the fingers in the hand. You could have these bent distortions. And these are the typical defects that one sees in liquid crystals. Okay? So since they are topological defects, they have charges. So that's a defect with a charge plus half, and that's a defect with a charge minus half. Okay? And they are formed by this combination of splay and bend. Okay? So they are inherent, but they can also be created by applying boundary conditions, which is just simple rubbing of the surface, and by a variety of choice of initial conditions. And one of our students had done a lot of work on these issues here. Okay? So now I'm not going to deal with pneumatic liquid crystals, okay? But I'm going to deal with these bent objects. Okay? So these are what go under the name of bent core liquid crystals. And now because they are bent objects and they are achiral objects, they have a curvature, they require two quantifiers. Okay? So one will be the director N, okay, which tells you about the natural direction of this arc, and the other one is the polarization. Okay, so that's the polarization, and the director is perpendicular to the polarization. So these are two perpendicular vectors. Okay, and because of the curvature, the pneumatic phase, it becomes unstable due to the formation of bent deformations in the N field. Okay, and a constant bend field cannot fill the space uniformly. Okay? So there are geometric frustrations, and these are resolved by the formation of what are called splay distortions in 2 dimensions. So that's a splay distortion in the xy plane, for example. Okay? Or they form these chiral twist bend structures. So that's what you see over here. Okay? And as you see, it could be a clockwise chiral or an anti-clockwise chiral. Okay? So that's what now gives chirality, which is constructed from these achiral objects. Okay? So these are the 2 phases that are important for us. We have the splay bend phase and we have the chiral twist bend phase. Okay? So what Nishant did was, very intensive molecular dynamics simulations, okay? And he constructed these curved objects using strings of beads. Okay, so this bent core unit that he constructed, it had 11 beads. Okay, you could have 15 beads or 17 beads. It only adds to the complication, and this is characterized by a bend angle chi. Okay, so this chi is decided by the curvature that you are assuming. Okay, and if you look at, so there exists a nice phase diagram for this particular system. Okay? So eta here is the concentration of the bent core molecules, and chi is the bend angle. So as you vary each of these, you go from you go through different kinds of phases. Okay, so this is the isotropic phase. You have the nematic phase where everything is aligned straight. In the smectic phase, you will have layers, okay, which have a certain arrangement. Then you have the twist bend phase, which is something like this. You have the splay bend phase, which is something like this, and this is another kind of a smectic phase. Okay, and as before, there will be 2 characterizations for this curved unit, the curved basic unit. One is the director n and a perpendicular vector, which is the polarization. Okay? So you consider lots and lots of these bent core units in a box. Okay? And then naturally you have an interaction between them. So this is a slightly modified Lennard-Jones potential. It's a Weeks-Chandler-Anderson potential, which takes into account not just the attraction between the molecules, but also takes care of the shape that the molecules have, because the molecules have to fit in a certain fashion to get appropriate phases. Okay? So now these n and p, these are vectors that one can write in terms of the pitch of each of these chiral objects that are formed. Okay, so here, for example, lambda s is the pitch of the splay bend, and lambda t is the pitch of the twist bend structure. Okay, and one can completely define np in terms of the pitch and the conical angle between n and the z-axis. Okay, so this, oops, I'm already here. Okay, so whatever. Okay, so these are the order parameters that one requires to characterize this phase, and here's the twist bend structure. Okay, so one nice aspect here is that you get the helix, and that is characterized by a continuous change of colors that one sees here. The splay bend phase will be characterized by alternating colors. Okay, so I won't go through the details because it's a real stress to fit everything in 8 minutes. So I'll just say that one nice thing that we noticed is that during this evolution, one could go to the twist bend phase via the splay bend phase, which was unexpected. Okay, so at intermediate times, one sees the splay structure, and then the equilibrated structure is the twist bend structure. Okay, and order parameters can be used to characterize it, but sadly, I can't go through all of it. Okay, and then this is the last slide maybe that I'll show, that there are lots of experiments nowadays where this kind of work is relevant. So these were rods which were heated, and as the temperature increased, one could get these different curvatures and one could get the different phases. And the next thing that we are moving on to is the formation of these baby skyrmion lattices. Okay? So hopefully the next time I come, I'll be better prepared for the 8-minute talk and tell you more about these fermion lattices. Okay, so I'll stop here.
We can take questions now.
Very interesting. Do you have any idea of what rheological properties this will have? Because these twist bend structures are known to show these shear
What,
thickening.
can you
Rheological properties of these materials, the twist bend structures show discontinuous shear thickening and so on. Does your theory predict anything about that?
We've not looked at that. We've just looked at the organization of the structures. Okay? But I think things like viscosity should play a role. Okay? But the model does not contain those parameters at the moment. So these are, these are very unusual structures. So the bent cores will align in the form of a structure like this, okay? And what is unusual here is that the polarization vector at the bottom points in a particular direction, but as you come up, it points in the opposite direction, okay? So that's why you call it a skyrmion. And these can be formed if you have thin slabs of bent core molecules. And it's also unusual that they form lattices. So there are a lot of experiments and a lot of knot theory which is being put into this. And that's something that we are now getting into. Okay.
Thank you. If no more questions, we can move to next speaker. Let's thank our speaker.
Thanks.